The equation of time describes the discrepancy between two kinds of solar time. These are apparent solar time, which directly tracks the motion of the sun, and mean solar time, which tracks a fictitious mean sun with noons 24 hours apart. Apparent, or true, solar time can be obtained by measurement of the current position, hour angle, of the sun, or indicated, with limited accuracy, by a sundial. Mean solar time, for the same place, would be the time indicated by a steady clock set so that over the year its differences from apparent solar time average to zero. The equation of time is the east or west component of the analemma, a curve representing the angular offset of the sun from its mean position on the celestial sphere as viewed from Earth. The equation of time values for each day of the year, compiled by astronomical observatories, were widely listed in almanacs and ephemerides. During a year the equation of time varies as shown on the graph, its change from one year to the next is slight. Apparent time, and the sundial, can be ahead, fast, by as much as 16 minutes 33 s, around November 3rd, or behind, slow, by as much as 14 minutes 6 s, around February 12th. The equation of time has zeros near April 15th, June 13th, September 1st and December 25th. Ignoring very slow changes in the Earth's orbit and rotation, these events are repeated at the same times every tropical year. However, due to the non-integral number of days in a year, these dates can vary by a day or so from year to year. The graph of the equation of time is closely approximated by the sum of two sine curves, one with a period of a year and one with a period of half a year. The curves reflect two astronomical effects, each causing a different non-uniformity in the apparent daily motion of the sun relative to the stars. The obliquity of the ecliptic, the plane of the Earth's annual orbital motion around the sun, which is inclined by about 23.44 degrees relative to the plane of the Earth's equator, and the eccentricity of the Earth's orbit around the sun, which is about 0.0167. The equation of time is constant only for a planet with zero axial tilt and zero orbital eccentricity. On Mars the difference between sundial time and clock time can be as much as 50 minutes, due to the considerably greater eccentricity of its orbit. The planet Uranus, which has an extremely large axial tilt, has an equation of time that makes its days start and finish several hours earlier or later depending on the time of its solar year orbital period. Sign of the equation of time. There is no universally accepted definition of the sign of the equation of time. Some publications show it as positive when a sundial is ahead of a clock, as shown in the upper graph above, others when the clock is ahead of the sundial, as shown in the lower graph. In the English-speaking world, the former usage is the more common, but is not always followed. Anyone who makes use of a published table or graph should first check its sign usage. Often, there is a note or caption which explains it. Otherwise, the sign can be determined by knowing that, during the first 3 months of each year, the clock is ahead of the sundial. The mnemonic NYSS, pronounced nice, for New Year, sundial slow, can be useful. Some published tables avoid the ambiguity by not using signs, but by showing phrases such as sundial fast or sundial slow instead. In this article, and others in English Wikipedia, a positive value of the equation of time implies that a sundial is ahead of a clock. History. The phrase equation of time is derived from the medieval Latin, equatio dirum equals equation of days. The word equatio was widely used in early astronomy to tabulate the difference between an observed value and the mean value, as in the equation of center, the equation of the equinoxes, the equation of the epicycle. Prior to the mid-17th century, when pendulum-controlled mechanical clocks were invented, sundials were the only reliable timepieces, and were generally considered to tell the right time. A description of apparent and mean time was given by Neville Maskelyne in the Nautical Almanac for 1767. Apparent time is that deduced immediately from the sun, whether from the observation of his passing the meridian, or from his observed rising or setting. This time is different from that shown by clocks and watches well regulated at land, which is called equated or mean time. He went on to say that, at sea, the apparent time found from observation of the sun must be corrected by the equation of time, if the observer requires the mean time. The right time was essentially defined as that which was shown by a sundial. When good mechanical clocks were introduced, they agreed with sundials only near 4 dates each year, so the equation of time was used to correct their readings to obtain sundial time. Some clocks, called equation clocks, included an internal mechanism to perform this correction. Later, as clocks became the dominant good timepieces, uncorrected clock time, i.e. mean time, became the accepted standard. The readings of sundials, when they were used, were then, and often still are, corrected with the equation of time, used in the reverse direction from previously, to obtain clock time. Many sundials therefore have tables or graphs of the equation of time engraved on them to allow the user to make this correction. The equation of time was used historically to set clocks. Between the invention of accurate clocks in 1656 and the advent of commercial time distribution services around 1900, there were 3 common land-based ways to set clocks. Firstly, in the unusual event of having an astronomer present, the sun's transit across the meridian, the moment the sun passed overhead, was noted. The clock was then set to noon and offset by the number of minutes given by the equation of time for that date. Secondly, and much more commonly, a sundial was read, a table of the equation of time, usually engraved on the dial, was consulted and the watch or clock set accordingly. These calculated the mean time, albeit local to a point of longitude. The third method did not use the equation of time, instead, it used stellar observations to give sidereal time, exploiting the relationship between sidereal time and solar time. Of course, the equation of time can still be used, when required, to obtain solar time from clock time. Devices such as solar trackers, which move to keep pace with the sun's movements in the sky, frequently do not include sensors to determine the sun's position. Instead, they are controlled by a clock mechanism, along with a mechanism that incorporates the equation of time to make the device keep pace with the sunday. Ancient history: Babylon and Egypt. The irregular daily movement of the sun was known by the Babylonians, and Book 3 of Ptolemy's Almagest is primarily concerned with the sun's anomaly. Ptolemy discusses the correction needed to convert the meridian crossing of the sun to mean solar time and takes into consideration the non-uniform motion of the sun along the ecliptic and the meridian correction for the sun's ecliptic longitude. He states the maximum correction is 813 time degrees or 5/9 of an hour, Book 3, Chapter 9. However, he did not consider the effect to be relevant for most calculations since it was negligible for the slow-moving luminaries and only applied it for the fastest-moving luminary, the moon. Medieval and Renaissance astronomy. There was much astronomical work on the equation of time between its discovery by Ptolemy and the Renaissance. Al-Batun, c9, Al-Khwarizm, c9, Kshya with Macron R, c10, Al-Ka with Macron Sh, c14, made improvements to the computation of solar longitude and the value of obliquity, and published tables of the equation, Taql al-Im Bilale, in their Zij, astronomical tables. After that, the next substantial improvement in the computation didn't come until Kepler's final upset of the geocentric astronomy of the ancients. G. J. Toomer uses the medieval term equation from the Latin equatio n1, for Ptolemy's difference between the mean solar time and the true solar time. Kepler's definition of the equation is the difference between the number of degrees and minutes of the mean anomaly and the degrees and minutes of the corrected anomaly. Apparent time versus mean time. Equation clock. Until the invention of the pendulum and the development of reliable clocks during the 17th century, the equation of time as defined by Ptolemy remained a curiosity, of importance only to astronomers. However, when mechanical clocks started to take over timekeeping from sundials, which had served humanity for centuries, the difference between clock time and solar time became an issue for everyday life. Apparent solar time, or true or real solar time, is the time indicated by the sun on a sundial, or measured by its transit over a preferred local meridian, while mean solar time is the average as indicated by well-regulated clocks. The first tables to give the equation of time in an essentially correct way were published in 1665 by Christian Huygens. Huygens set his values for the equation of time so as to make all values positive throughout the year 11 and 2. Another set of tables was published in 1672-73 by John Flamsteed, who later became the first Astronomer Royal of the New Greenwich Observatory. These appear to have been the first essentially correct tables that gave today's meaning of mean time, rather than mean time based on the latest sunrise of the year as proposed by Huygens. Flamsteed adopted the convention of tabulating and naming the correction in the sense that it was to be applied to the apparent time to give mean time. The equation of time, correctly based on the two major components of the sun's irregularity of apparent motion and 3, was not generally adopted until after Flamsteed's tables of 1672-73, published with the posthumous edition of the works of Jeremiah Horrocks. Robert Hooke, 1635-1703, who mathematically analyzed the universal joint, was the first to note that the geometry and mathematical description of the non-secular equation of time and the universal joint were identical, and proposed the use of a universal joint in the construction of a mechanical sundial. 18th and early 19th centuries. The corrections in Flamsteed's tables of 1672/3 and 1680 gave mean time computed essentially correctly and without need for further offset. But the numerical values in tables of the equation of time have somewhat changed since then, owing to 3 factors. General improvements in accuracy that came from refinements in astronomical measurement techniques. Slow intrinsic changes in the equation of time, occurring as a result of small long-term changes in the Earth's obliquity and eccentricity, affecting for instance the distance and dates of perihelion, and the inclusion of small sources of additional variation in the apparent motion of the Sun, unknown in the 17th century, but discovered from the 18th century onwards, including the effects of the Moon and 4, Venus and Jupiter. From 1767 to 1833, the British Nautical Almanac and Astronomical Ephemeris tabulated the equation of time in the sense mean minus apparent solar time. Times in the almanac were in apparent solar time, because time aboard ship was most often determined by observing the Sunday. In the unusual case that the mean solar time of an observation was needed, one would apply the equation of time to apparent solar time. In the issues since 1834, all times have been in mean solar time, because by then the time aboard ship was increasingly often determined by marine chronometers. In the unusual case that the apparent solar time of an observation was needed, one would apply the equation of time to mean solar time, requiring all differences in the equation of time to have the opposite sign than before. As the apparent daily movement of the Sun is 1 revolution per day, that is 360 degrees every 24 hours, and the Sun itself appears as a disk of about 0.5 degrees in the sky, simple sundials can be read to a maximum accuracy of about 1 minute. Since the equation of time has a range of about 33 minutes, the difference between sundial time and clock time cannot be ignored. In addition to the equation of time, one also has to apply corrections due to one's distance from the local time zone meridian and summer time, if any. The tiny increase of the mean solar day itself due to the slowing down of the Earth's rotation, by about 2 milliseconds per day per century, which currently accumulates up to about 1 second every year, is not taken into account in traditional definitions of the equation of time, as it is imperceptible at the accuracy level of sundials. Explanations for the major components of the equation of time. Eccentricity of the Earth's orbit. Graph showing the equation of time, red solid line, along with its 2 main components plotted separately, the part due to the obliquity of the ecliptic, mauve dashed line, and the part due to the Sun's varying apparent speed along the ecliptic due to the eccentricity of the Earth's orbit, dark blue dash and dot line. The Earth revolves around the Sunday. As seen from Earth, the Sun appears to revolve once around the Earth through the background stars in 1 year. If the Earth orbited the Sun with a constant speed, in a circular orbit in a plane perpendicular to the Earth's axis, then the Sun would culminate every day at exactly the same time, and be a perfect timekeeper, except for the very small effect of the slowing rotation of the Earth. But the orbit of the Earth is an ellipse not centered on the Sun, and its speed varies between 30.287 and 29.291 km per second, according to Kepler's laws of planetary motion, and its angular speed also varies, and thus the Sun appears to move faster, relative to the background stars, at perihelion, currently around January 3, and slower at aphelion a half year later. At these extreme points this effect varies the real solar day by 7.9 seconds per day from its mean. Consequently, the smaller daily differences on other days in speed are cumulative until these points, reflecting how the planet accelerates and decelerates compared to the mean. As a result, the eccentricity of the Earth's orbit contributes a sine wave variation with an amplitude of 7.66 minutes and a period of 1 year to the equation of time. The 0 points are reached at perihelion, at the beginning of January, and aphelion, beginning of July. The extreme values are in early April, negative, and early October, positive. Obliquity of the ecliptic. Sun and planets at solar midday, ecliptic in red, Sun and Mercury in yellow, Venus in white, Mars in red, Jupiter in yellow with red spot, Saturn in white with rings. However, even if the Earth's orbit were circular, the perceived motion of the Sun along our celestial equator would still not be uniform. This is a consequence of the tilt of the Earth's rotational axis with respect to the plane of its orbit, or equivalently, the tilt of the ecliptic, the path of the Sun seems to take in the celestial sphere, with respect to the celestial equator. The projection of this motion onto our celestial equator, along which clock time is measured, is a maximum at the solstices, when the yearly movement of the Sun is parallel to the equator, causing amplification of perceived speed, and yields mainly a change in right ascension. It is a minimum at the equinoxes, when the Sun's apparent motion is more sloped and yields more change in declination, leaving less for the component in right ascension, which is the only component that affects the duration of the solar day. A practical illustration of obliquity is that the daily shift of the shadow cast by the Sun in a sundial even on the equator is smaller close to the equinoxes and greater close to the solstices. If this effect operated alone, then days would be up to 24 hours and 20.3 seconds long, measured solar noon to solar noon, near the solstices, and as much as 20.3 seconds shorter than 24 hours near the equinoxes. In terms of the equation of time, the inclination of the ecliptic results in the contribution of a sine wave variation with an amplitude of 9.87 minutes and a period of a half year to the equation of time. The 0 points of this sine wave are reached at the equinoxes and solstices, while the extrema are at the beginning of February and August, negative, and the beginning of May and November, positive. Secular effects. The two above-mentioned factors have different wavelengths, amplitudes, and phases, so their combined contribution is an irregular wave. ET equals apparent mean. Positive means, Sun runs fast and culminates earlier, or the sundial is ahead of mean time. A slight yearly variation occurs due to presence of leap years, resetting itself every 4 years. The exact shape of the equation of time curve and the associated analemmas slowly change 16 over the centuries, due to secular variations in both eccentricity and obliquity. At this moment both are slowly decreasing, but they increase and decrease over a timescale of hundreds of thousands of years. When the Earth's orbital eccentricity, now about 0.0167 and slowly decreasing, reaches 0.047, the eccentricity effect may in some circumstances overshadow the obliquity effect, leaving the equation of time curve with only one maximum and minimum per year, as is the case on Mars. On shorter time scales, thousands of years, the shifts in the dates of equinox and perihelion will be more important. The former is caused by precession, and shifts the equinox backwards compared to the stars. But it can be ignored in the current discussion as our Gregorian calendar is constructed in such a way as to keep the vernal equinox date at March 21, at least at sufficient accuracy for our aim here. The shift of the perihelion is forwards, about 1.7 days every century. In 1246 the perihelion occurred on December 22, the day of the solstice, so the two contributing waves had common 0 points and the equation of time curve was symmetrical. In astronomical algorithms, Ms gives February and November extrema of 15 minutes 39 sec and May and July ones of 4 minutes 58 seconds. Before that time the February minimum was larger than the November maximum, and the May maximum larger than the July minimum. In fact, years before 1900 or 1900 BCE the May maximum was larger than the November maximum. In the year 2000 the May maximum was plus 12 minutes and a couple seconds while the November maximum was just less than 10 minutes. The secular change is evident when one compares a current graph of the equation of time, see below, with one from 2000 years ago, e.g., one constructed from the data of Ptolemy. If the gnomon, the shadow casting object, is not an edge but a point, e.g., a hole in a plate, the shadow or spot of light will trace out a curve during the course of a day. If the shadow is cast on a plane surface, this curve will be a conic section, usually a hyperbola, since the circle of the sun's motion together with the gnomon point define a cone. At the spring and fall equinoxes, the cone degenerates into a plane and the hyperbola into a line. With a different hyperbola for each day, hour marks can be put on each hyperbola which include any necessary corrections. Unfortunately, each hyperbola corresponds to 2 different days, one in each half of the year, and these 2 days will require different corrections. A convenient compromise is to draw the line for the mean time and add a curve showing the exact position of the shadow points at noon during the course of the year. This curve will take the form of a figure 8 and is known as an analemma. By comparing the analemma to the mean noon line, the amount of correction to be applied generally on that day can be determined. The equation of time is used not only in connection with sundials and similar devices, but also for many applications of solar energy. Machines such as solar trackers and heliostats have to move in ways that are influenced by the equation of time. Civil time is the local mean time for a meridian that often passes near the center of the time zone, and may possibly be further altered by daylight saving time. When the apparent solar time that corresponds to a given civil time is to be found, the difference in longitude between the site of interest and the time zone meridian, daylight saving time, and the equation of time must all be considered. The equation of time is obtained from a published table, or a graph. For dates in the past such tables are produced from measurements done at the time, or by calculation. For future dates, of course, tables can only be calculated. In devices such as computer-controlled heliostats the computer is often programmed to calculate the equation of time. The calculation can be numerical or analytical. The former are based on numerical integration of the differential equations of motion, including all significant gravitational and relativistic effects. The results are accurate to better than 1 second of time and are the basis for modern almanac data. The latter are based on a solution that includes only the gravitational interaction between the Sun and Earth, simpler than but not as accurate as the former. Its accuracy can be improved by including small corrections. The following discussion describes a reasonably accurate, agreeing with almanac data to within 3 seconds of time over a wide range of years, algorithm for the equation of time that is well known to astronomers. 19. It also shows how to obtain a simple approximate formula, accurate to within 1 minute of time over a large time interval, that can be easily evaluated with a calculator and provides the simple explanation of the phenomenon that was used previously in this article.